Right, it's 10 past 10, so I'm going to go get started. Good morning, everyone, and welcome to day 2 of our online course delivery. I hope you are all doing fine. I'm going to get started by having a little bit of check on how things are with you. And I'm going to use the group chat for posing a couple of questions, and so you can go ahead and answer them. If I can get my mouse to move over to the place where I would like it to go to. And so the first question I have is, I know people are in different places, and so I want to know what the weather is like where you are. You don't need to tell me where you are, but just tell me what the weather is like. How is the weather where you are? And the answers that are allowed for this is, or one word answer. Foggy, snowy, rainy, sunny, and if it is something else, you can go ahead. But I just want to see how things are. And because there was a snow in Pullman last night, and so I've got different answers here. I'm going to give you 30 seconds, and people are joining in. So the question is, what's the weather like where you are? Okay, very interesting. A good number of places it's snowing and cloudy in some places, and that sounds like Pullman. Okay, I guess we got a sense of the weather. There is no place where it is sunny. So my next question is going to be this: did you have your coffee for the morning? I don't know if I have spelled it right. The answers are yes, not yet, I don't drink coffee. Okay. Okay. All right. So we've got a good number of people who don't drink coffee. That's very nice to know. I never knew that. I drink coffee. I enjoy coffee, and I've had a couple so far. Okay, next time when I want to ask this question, I'll have, did you have coffee or tea would be the better way to ask, and I will get yes or no for the most part, it sounds like. All right, I think we're in good shape and people have joined, so I'm going to get started with today. Is the slide the way it should be? Last time I forgot to change from what I see on as a presenter, and I was apologize for those of you who had to struggle through it, but I think it worked out fine. But today I think it sounds like it is the right way. Zoom has been good, I think, and the recordings have come in time. So when we had the discussion last time, I did get it, the same day, and I have put it on Osbol, and you probably have seen them. And later during the day, they would send one that has got a transcription of what the audio was like. And so if you go check now, you actually see that, and it's helpful, but sometimes some of the words get something else, which things that I haven't said, and I'm not going to go edit them. So use them as you find them useful. But for those of you who are not able to join online or have some internet connection problems and things are not streamed, I think that would be a good thing to have. And so we'll continue to do what we are doing, and I very much appreciate your responsiveness and your participating in a good way. When you have a question, as I discussed, if you have a question that is kind of difficult to put on the group chat, you should unmute yourself and tell, but otherwise I think we'll use the group chat. I'll keep my eye on there, and James has joined us also, and so he may keep an eye on it, but I'll try to make sure that as I discuss, I will pay attention to what happens there. And if you need to grab your coffee, you should feel free to do that as we discussed, but don't be away for a long time. So we're going to continue this, and I have asked you a couple questions on survey. You have participated, and especially on the question of exam. That was one of the things that I would like to get your feedback on. And then you have, and if you didn't get a chance to do that, make sure that you respond to that survey. But what I have out of it so far, at least for that specific question on how you would like midterm 2 to be, is split. A slightly higher proportion who want to have take home, but otherwise it's kind of split. And I'm leaning towards take home, but I need to define what take home means now. And there were some interesting questions people have asked, because the definition of home in the situation we are now in is slightly different. So I'm not going to expect you to take it home as wherever you are and so. No, I mean not online. You would submit it on Oswald and you will get a 24-hour time is what I really mean. So if that was a question you have, and then if it is online or offline, then I think the difference would be the nature of the questions. And I think if it is going to be offline, it will be more of the homework type problems that you would solve, or probably slightly harder. If it is online, then they would be fill in the blank or true and false type problems. So I haven't made up my mind. Let me hear a little bit more from you, and hopefully by Friday we will decide one way or another. Whichever way it goes, you don't need to worry. It's just more of a format and how things will best be organized. Otherwise, there isn't going to be too much of a change on your preparation or how you would handle it. I worry more about the people who have unstable internet connection, and that makes the online version not a good solution. I would like to be fair to everybody, and you get a chance to think through things. And if you really want to take advantage of having to learn from it, I think the offline one probably will work better for you. All right, that's where we are, and we're going to get started. And thanks again for those who have completed the survey. So we're going to continue discussing Turing machines today. And let me get to this place where I can move things around. What we did in the last lecture was have like an informal description of what Turing machines are. I think that's a good way to start. And then we had this control and the tape head that moves around it. And then we formally defined what a Turing machine is. And then we looked at much like what we did with finite automata, to think of them as transition functions being things that would take us from one configuration to another one. We specifically defined what configurations mean in Turing machines. So this is what the current state is, what the current content of the tape is, and where the head is. These three together would constitute a configuration. And so the machine would go from one configuration to the next, and that's how we would consume the input or read the input and come to a decision whether to accept or reject. That's how Turing machine computation happens. And then I finished off with a couple of slides that talk about recognizable and decidable language. We actually didn't get time to get into that one. So I'm going to start with a few slides just to have a reminder for what we did. And I'm going to go fast on them. And then we will start with what I would like to do today. And so there will be a few slides now, reminders, if you like. And so the formal definition of a Turing machine is a 7-tuple, and here's what the list is. We've got the states, the set of states Q, we have the input alphabet sigma, and the tape alphabet tau, and there was some good discussions and what people were asking on the chat last time, what the difference between the two is. So the input alphabet is a subset of what the tape alphabet is. The Turing machine has an ability to write onto the tape, and therefore there could be more symbols. But at the minimum, it will have this blank symbol that we decided last time, the half cup. For those of you who drink coffee, that looks like a cup. That is the end marker where the input end is indicated. And so at the very least, it will have that one. And so that is a member of the tape alphabet. But other than that, the input alphabet is a subset of the tape alphabet, would be a fair thing to say. The transition function would take us from what state we are in and what the content of the tape is, and it will take us to another state, some changes to the tape. And in addition to that one, we will make the head of the tape to move left or right. And so this is part of the transition function. Other than that, we've got the initial state or the start state, and we have distinct, reject, and accept states. Unlike finite automata that we know from before, where we have just accept, now we have an explicit reject. So that was the formal definition. And this is the slide that I relied on you to look on yourselves, but these are some terms. I just wanted us to remember them so we know what the configuration is. So the start configuration will be where the start initial state is. Otherwise, we have the input. That's how the configuration is, and this would evolve over time, and we have the accepting configuration and the rejecting configuration. When it is one of these, accepting or rejecting configurations, we will say that this is a holding configuration. Otherwise, it will be a Turing machine that runs forever. And the formal way to say what a Turing machine M accepts is when we have these configurations, K of them, and we have a way to yield from CI to CI plus 1, starting with the input on the input string W, and the final state CK is an accepting state. That's when we say the Turing machine accepts the input string W. We still are on having kind of looking at slides from last lecture, and so that's the reason I'm going a little bit fast. Here is a place where we needed to define two things. And I wanted to, I've told you already informally a little bit, but we say a language recognized by a Turing machine M, we will call that, we will denote it by L of M. That's the language of that Turing machine. And it is recognizable. We will call the language recognizable by a Turing machine if there exists some Turing machine that recognizes it. Some other books, not ours, some other books would call this language recursively enumerable language. And I just want you to know that term. You don't need to know why they are called that way, but they are enumerable language in a recursive fashion. And so a Turing recognizable language is also known as recursively enumerable language. So when we have a Turing machine and it starts with an input, there are three possible outcomes. I've told you this before: accept, reject, or it runs forever, or it loops, or it doesn't hold. And so it could fail to accept an input, a Turing machine, by either explicitly entering into the reject state or by having to fail to stop by looping. And sometimes we want to make a distinction, and we have a reason for wanting to do that, to know whether it is looping and it is not ending, or whether it was something that was going to reject. And so for this reason, we prefer sometimes Turing machines that hold on all inputs, and they would be called deciders. So now we are making a distinction between recognizable and Turing decidable language. And so a language that is Turing decidable is also known as recursive language, okay? Not recursively enumerable, but just recursive language. And so this was the picture I left you with last time. And I've redrawn it just a little bit now to see that there are languages that are decidable, and there are languages which we will learn next week that are not decidable by a Turing machine, but they are recognizable. And so there won't be anything that will not be Turing recognizable. As we have agreed last time, Turing machines are as powerful as what real computers can do. And so a Turing machine recognizable will be our universe, so to speak. And we will look at decidable language and things, examples of them today, and we will learn about language that are not decidable by a Turing machine, but they are still recognizable in what is going to come. So this was just a reminder of where we were and things that we didn't get a chance to at least formally go through in our last lecture. Today we'll be looking at examples. And so there was an informal description or discussion of what Turing machines are. We gave formal definitions and have some terminology set for ourselves. But like we have seen with finite state machines, NFAs and DFAs, and like we've seen in push-down automata, we're going to be now looking at what a Turing machine is and to try to design them. And so what I will do now, and I want to begin by a note, is we have already in our last lecture seen what I call, or what CptS calls, a higher level description of Turing machines. And they are precise enough for what we want to do. They are easy to understand, and they would come closer to what you as computer scientists would know in terms of having to write algorithms or implement them or write programs. And so for that reason, that will be my preference. But I'm going to use one or two examples where we will actually go down and look at how they would look like if we were to care about giving a formal description. By formal description, I mean go back to those 7 tuples and give me all those 7 elements, including the transition function in its fullness. And so the book encourages you to be convinced that these higher level descriptions are just a shorthand. And it's actually a good way to think of it. And this is what I would want you to remember also. There is a reason why you're taking a theory class. And so we are now trying to say, if our machine was reduced to what we are seeing now with a control, a tape, and a tape head, and we are going to solve problems using it, and we don't know anything else. Nobody has written some high-level functions for us. Nobody has written an operating system for us. We're not going to have a programming language. We are just given this thing, and it could have been a mechanical device. And think of like what you would do if you had a sewing machine, or if you were to draw water from a well, and then you had a lever, and you have to move things yourself, and you have to drop the bucket. So at the very lowest level is where we are. And some of you might actually have done some assembly language programming, for example. You're coming closer to what the machine looks like, and you write things like that. So it's a shorthand means, if we cared and if we wanted to get to the lower level, we would have, but there is a higher level abstraction or description that we are giving. That's the one I would prefer, and the book prefers, and we will give, but we'll give 1 or 2 examples. We'll go down to saying them in full. So our first example is going to be a Turing machine, and I call it example 1, and I call the Turing machine M2, and you will discover in a second why it's called M2, why it's not called M1, because we reserved M1 for an example we have seen last week. So we're going to design a machine, a Turing machine, and we'll call it M2, that would help us decide whether we have this language A that consists of zeros, but its length is a power of 2. So A is 0, and that's my PowerPoint version of 2 to the power of n is what I'm trying to write. But if you write another power there, kind of gets messed up. So I wrote it this way. So 2 to the power of n is the length of 0. So we've got 0 repeated a power of 2 times. In other words, the length of that string is of power 2. Now you know what a Turing machine is. That's all you have. How would you go about solving this problem? So this is a question. So this is a place where I would at least expect somebody to say something on the group chat. I'll keep an eye for that one, and I'm going to give you 15 to 30 seconds for somebody to say something. So I want to ask to come up with a strategy, and you will see this thing running through the examples I would be presenting today. We need to find a way. If this is all we have, and I want to know a string, I know it's all about zeros, and I'm going to decide whether I'm going to say the string that I'm reading is a member of this language. That's a decision problem I have, and I have this head, the tape head that I can move around. I could, do something with it, but I want to decide. I want to determine whether the length of these, the zeros that I'm reading, is a power of 2. The length of it is a power of 2. If that's what you had, and this is the machine you have, how would you go about doing it? How would you about designing a machine that will do this? So let me see if there is anybody who would give some thought to this one. I'm going to give another 20 seconds maybe for people to come up with a suggestion for how to go about solving this problem, decide whether the length is a power of 2 or not. Okay, I didn't see any volunteers, so I'm going to go tell you how we will do this. So we're going to have a strategy that would help us answer this question. And so we will take several swaps through the input. And every time we do, we're going to reduce the number of zeros by half. And so we'll sweep left to right across the tape, crossing every other zero. And so when we cross that one, then we come to the next stage. If the tape now contains a single zero, after we have crossed off this, every other zero, and we'll come back and repeat this thing, and we are going to cross off every other zero. And so by the time we come back to this stage, if we have one left, then we will accept it. There is a single zero left, then we will accept it. If in stage one the tape contained more than a single zero and the number of zeros was odd, then there is no way the original number could be a power of 2. It could be even, and therefore we would reject. So after we have done this one, then we have finished one iteration of swapping through and crossing off every other non-zero. And so we'll come back to the left-hand end of the tape and then do this all over again. And so we go to stage one, cross off, and then see how this one goes. What I have shown on the right tells you how this procedure is working, how this approach, how this strategy is working. So we had originally, like, let's say 16 zeros. And so the next time we would reduce by crossing off half of them, would reduce it to 8 by crossing off the other half. Would reduce to 4, to 2, and then we'll finally get to 1. And so the final step 1 is the place where we would stop. So you can think of this one as something that you have implemented in a recursive fashion in a way. And so each iteration cuts the number of zeros we have by half, and we will stop when it is 1. In fact, this one would work even if we had just a single zero. A single zero in this language will be a valid member. It just has 1. It's 2 to the power of 0 will be a 1. And so we've got 0 of length 1. And that will be accepted immediately. And we don't have to even iterate. But if we have any other number, then it will work. If it was not a power of 2, then stage 3 will discover it, and then it will be rejected. So this is a high-level description. And we wanted to begin with this one, and for the most part, we'll be satisfied with a description of this kind for the purpose of what we have for this course and for many other interesting problems that would come later on. But we want to see now how this might actually, if we cared, been implemented or formally described. And here is what the machine now looks like. We still have M2, and we've got these 7 tuples that we want to faithfully kind of describe them one by one, and then here we have them. So the number of states now, we have the start and the accept and reject the states that we would expect. But other than that, you do not necessarily immediately now see that you need 5 states. And this will be something that will come out only after we have started to formally describe them. So the informal description we gave in the previous slide doesn't have anything about states, and so it's not going to tell us what is needed. So this is going to be clear when I show the next slide, but there will be some 5 states that we will need other than, or 4 additional states other than the start state to be able to completely describe this one in a formal way. The input alphabet, as you know, is just 0, and the tape alphabet now has 0 and the blank one to indicate that it is an int. But if you remember, we were crossing off these zeros, every other 0 that we got in each of these iterations, and so we need another symbol there. That's an x1 to show this one. The transition function, the best way for us to see this one, we could also have it in the form of a table, would be to draw a state diagram, which is what I will do. And so we have the start, accept, and reject states with Q1, Q accept, and Q reject. And so here will be the formal description. So the main big issue we have to do, it will be to describe what the state diagram would look like. And that will be our description here. Because we have now decided for this particular example to give a complete state diagram, just like what we have done with NFS and DFS, we have to remind ourselves of some notations, and you will hopefully be convinced that we needed as many as those states that we had shown in the previous slide. So we have Q1, that is our initial state, and if you remember, we wanted to know, to come back after we have done one of the iterations where we crossed off every other zero, we come back. So we would like to know where the left end of the tape is, because we don't want to get past of it. And so in this particular design, we have come to indicate that by having a special symbol. And that symbol will be the blank symbol, the very symbol that we use to indicate the end of the input string. That was a blank. We're going to use it in an additional meaning now to show that we are at the end of the tape, the left end of the tape. And that's the reason why we have this transition from Q1 to Q2. The only thing that's happening between Q1 and Q2 is that we have moved the tape head to the right, and we wrote the symbol blank. That's what the arrow 0 going to blank and R shows you in that transition. This is what has happened. And the reason for this one, I've written it down in green at the bottom. This machine begins by writing a black symbol over the leftmost 0. This is interesting for us because it's the end of the input, the left end of the input, so that it can find the left-hand end of the tape in stage 4. When we come back to do stage 4, if you remember, was where we had to return to the head of the left-hand end of the tape. That was what stage 4 was, and that is what is needed. The rest of it will be clearer as we gaze at it for a second. So remember what we were doing with push-down automatas when we had these transition functions. We were saying, you know, what would happen to the stack, what would happen to the tape. And similarly here, we would show what is on the tape on the left end of the arrow. And then what we have on the right will be to show us what will happen to the tape, what it gets written, and whether the tape is going to move to the left or the right. That's what the L and R's would show you. So we have taken care of the first arrow there, and Q1 was the initial state. And if there wasn't, remember what we are trying to do with this machine, if there wasn't any 0 to worry about, if there was, you know, no length in a way, then we would move to the right and reject it. That's easy. But the rest of it, whether we have a power of 2 or not, is going to be determined by the rest of these transitions. And so we're in Q2 now, basically means we have to start our crossing of zeros every other one that we see. And that's what is happening between Q2 and Q3. So we read a 0, we marked it off, and then we moved the tape to the right. And we will stay in Q3 as long as we have this condition going on by successfully crossing off a 0 every time we see a 0 and repeating it there. There is a shorthand written there. So when we are in Q3, we wrote X, and then we write we were telling that the tape head is moving to the right, but we didn't explicitly write down there that we are writing without having to do anything on the tape is what we mean there. And so that is a shorthand. Otherwise, the rest of the transition functions that you see, the arrows there, should be self-explanatory. Whatever you see on the left is what is read, and what you see on the right is what has happened to the tape. We mark it off, we move to the right. We mark it off, we move to the right. And we will accept when we have found, when we have iterated through these ones, several iterations have happened, likely, and when we have found a situation where there is only 1 0 left, then when we accept it. So see, this is what the state diagram would look like. This will be the only one where I will go to this much of a detail to tell you, and this is a complete description. All of the states that are involved are shown. What is taking us from one to the other is shown. And this was a fairly simple problem, or somewhat simple problem, and so we needed only this many states. But you can imagine now, if we have to design a Turing machine for more complex tasks, as we will see for a couple examples today, then this is not going to be something we would like to do. It will get very complex and to some degree unnecessary to do. And so I've got a run so that you do this for yourself. And I have shown you here how this Turing machine will work if we were to run it on this particular input that has got a 0 of length 4 zeros. And so it's a power of 2, but you can see now even for this one, that would require only, how many iterations would it require? So it will cross off every other 0 in one iteration, and then it will come back and cross off another of the 2 that are left, and so it will require 3 iterations. Even for this one, you see how many of these states and how the tape movement is happening, and the way to read this one will be to first read it downwards. And so on original, the initial configuration will be Q1, that's our start state, and we've got the input, all of it. And then the next thing that has happened is we just marked that this is the end of the left end of the tape with a blank, and we moved on to state Q2, and we have the rest of the other zeros remaining, and then everything else that happens from then on will be to cross off zeros as we proceed, and then we go to the next state. We go to the next state by moving the tape head to the right. So the way to read this one will be first downwards, and then when we finish the first column, you go to the next one, and you get to the third one finally. And you will be, I'm sure, when you get your tea or coffee later on, you'll make sure that you can follow along this one, and this machine would accept this input as it should, because it has got an input of length 4, the zeros of length 4, which is a power of 2. All right, that was example 1, and I hope you have followed me along. Example 2 is going to be a familiar one, and this was why I told you we will call this thing in reverse order. And the machine we saw last time looked at this example. We used this example to informally describe what a Turing machine was. And we had a test of a membership in this language, and we called this language B. It involved a string W that is binary. It's either a 0 or a 1 of any length. And we've got this hash symbol in between, and what is to the left and to the right of this hash symbol was the same. So we used that example to describe what a Turing machine for this one would look like. And what we want to do today, and in this example, will be to turn that informal description into a formal description, just like what we did with example 1. So this was what it was. And if you remember, we came up with an algorithm or with a description for this one, and that description was to kind of go in a zigzag fashion by having to read the first element to the left of the hash symbol, compare it with the first element we see in the right. And if these two are not the same, there is no business for us to continue. And so we go ahead and reject. Otherwise, we move and then compare the other two, and then we proceed. That was the general idea. We were zigzagging across the left and right sides of the hash symbol, and we would find, or we would reject the first time we found dissimilarity. Otherwise, we would keep on doing this one. So this was a repetition of what we said then. And so there were a couple opportunities for us to reject. Otherwise, if everything has gone fine, we would accept it. It has only 2 states, and it was intuitive. And I am describing it fairly quickly now because we saw it last time. And we'll quickly now see how much more complex it will get if we are going to design a complete or a formal description of this Turing machine. But we'll try, we will do, and let me do it more like 75% complete compared to what we had done for the first example. And so our machine is called M1. It has got the 7 tuples, just like what we had before. And this time we are going to need more states because there are more things to worry about as we do the crossing of things. And the input was 0, 1, and the hash symbol. That was the input alphabet. The tape alphabet had this, and in addition to it, we've got the end symbol, the blank, and then we had this cross off that we do. And the cross off was for having to make sure that we are tracking things and making sure that they are equal. And so we had this tau, and that alphabet is described in this fashion. The transition diagram, we will do it or the transition function, we will use a state diagram to show. Other than that, we've got the start and the accept and reject states like what we had before. So I'm going to, we've given names to things here, and I'm going to begin by telling you this state diagram. And I'm not sure how long ago it has been where you had visited your eye doctor, but this is a taste of your sight. And so the first question I have is, does anybody see Q reject in this state diagram? And then I'm going to look for some participation. If there is anybody who sees a Q reject, say yes. And I'm going to give you 20 seconds. So while you do that, you just gaze at this one for a second, and I'm going to try to explain after we get a chance to see it. But the first question I have is, this is a state diagram, and we have seen in the previous slide this zigzagging and crossing of marks to having to check equality will make us go require as many as 8 states, and this is what the state diagram looks like. But we had defined what Q reject, or we had introduced what Q reject and Q accept are, and then I wanted to see if you see Q reject in this state diagram. Okay, so that looks like there is nobody who saw a Q reject there, and it's not a mistake, it's not a typo there, it's just because it's not drawn. And the reason it's not drawn is because the book wanted, and I think it makes sense to have to not make this one overly complicated. It's already fairly complicated, but not overly complicated. So we'll go through, and I will highlight a few things here, but there is a reject state. It's just that it's not shown there. For example, if you were in Q5 and you get the hash symbol, and then that would take you to a reject. Those type of things which are not explicitly shown here is where the Q rejects would come. So there are a few, including the one that I just mentioned now, that are not shown in this state diagram explicitly, but they are implicitly there. Okay, so what do we have? We have the first stage that was going through crossing of things is implemented through the first 7 states, and the last one is where the second stage is shown. And so the first and second stages were, to just remind you, we're zigzagging and to see the corresponding positions on either sides of the hash symbol to check whether their inner positions contain the same symbol. If they don't, we reject. Otherwise, we keep on checking to keep track of which symbols correspond. And this was all happening in stage 1. The second stage was when all symbols to the left of the hash symbol have been crossed off, we check for any remaining symbols. That means there was some extra, for example, on the thing on the right-hand side of the hash symbol was longer. And if there is anything remaining, that means they were not even equal in size, we reject. Otherwise, we would accept this, how this was going. So all of the states that are up to 7 are showing you this. And I don't know what else I want to tell you other than this one. So one thing you would notice is the state diagram here looks symmetric. And so the problem itself had to do with having a hash symbol in the middle and then seeing how things are to the left and the right. So the state diagram reflects the fact that we are looking at things and crossing off in corresponding positions. One thing, what happens when we read a 0 and moving to the right, and the other one is when we read a 1 and we still move to the right. So remember, the input alphabet has only 0s and 1s, and so we are going tracking things that begin with a 0 and tracking when they begin with a 1. And so that is what you see from this diagram. The rest of it is much like what we have seen in the previous diagram, where the notation for our transition from one state to another will show us what the current input is, the tape head, and then what is going to happen when we read that input. What we write on it, the cross-off marks, is what you see on the X, and whether we are moving to the left or to the right is what you see. Other than this, I don't know what want to tell you other than what I have pointed out. I think this probably would be enough. And the rest of it is for you to look at and then convince yourself that you agree with when it is accepted. The high-level description was clear enough, and we have seen it last time. All right, I'm going to move on and look at the third example, and we've got 10 minutes and I've got 2 examples left. Fortunately, for the 2 examples that are left now, we're not going to do the state diagram descriptions. And so we are going to suffice with the high-level description. Okay, so we saw one example where we decided lengths of an input string, and so we were able to use our Turing machine to determine whether the length was a power of 2. The other one had to make us look at the string and then look at to the left and the right and make sure that corresponding positions are the same. In other words, the symbol to the left of the hash symbol and the string to the right of the hash symbol were equal. Now we're going to do arithmetic, and great, we're going to multiply, in fact. And so we're going to design a Turing machine M3 that decides whether a string that we read is a member of this language. And our language now is called C, and it has got 3 alphabets, A, B, and C, symbols, and they are repeated a certain number of times. A is repeated I times, B is repeated J times, C is repeated K times. And what qualifies for a string to be a member of this one is the product of I and J is equal to K. And we are going to require that I, J, and K are each greater than 1. So basically, we have things to keep track of, that they are A, B, C, and we have some numerical computation, some arithmetic to be done. The I's and the J's, their product is equal to K is what we want to go to do. If I had a lot of time, I would have probably said, here is a good time where somebody would come up with a strategy for how to go about this one. But because we don't have a whole lot of time, we'll work through this together. And so I'm going to give a high-level description here, and that's where we'll be stopping. So remember what we are doing, and I have tried to remind ourselves the language we are trying to, this Turing machine is trying to decide at the left bottom corner of the slide. So we have A to the I, B to the J, C to the K, and the product of I and J is equal to K is the condition we want to look for. And so we're going to scan the input from left to right. This high-level description has got 4 states, and we're going to scan the input from left to right to determine whether it is a member of this A plus, B plus, C plus, and reject if it isn't. And so what this one is basically doing is taking care of the base case, or where I, J, and K are all 1, and we want to make sure that A to the, this thing is, if it's a member of this language. So this one looks like what we have seen in regular expressions. We have at least one A, at least one B, at least one C is what the plus signs there mean. And if the input is different from this one, then we are going to immediately reject it, okay? And so that's what stage 1 does. Stage 2, and from here on, is where the math would begin, where the multiplication would actually be checked. So we return to the head of the left-hand end of the tape. We have made sure that it at least satisfies this one, that it consists of A's, B's, and C's, and at least one of them each is what has happened. If this one was not satisfied, the calculation will not be needed. And so we come to the left-hand end of the tape, and then we start now making sure that the product will, the product of I and J would be equal to K, where I and J are the powers of A and B, or the repetitions of A and B. So we cross off an A and scan to the right until a B occurs, because we expect a corresponding B to match it against, to see if the product would be a K. So we cross off an A and scan to the right until a B occurs, and we shuttle between the B's and the C's, crossing off one of each until all B's are gone, that we have exhausted them. And if all the C's have been crossed off and some B's remain, then that product will not be equal to the product of I and J will not be equal to K, and therefore now we have an easy way for us to say reject. That doesn't add up. That multiplication is not correct, and so we reject. Otherwise, we restore the crossed off B's and repeat stage 3. We do exactly the same thing that we have done if there is another A to cross off. So the first time we crossed off an A and found a matching B for it. And so we will do the same thing now and repeat stage 3 if there is another A to cross off. If we have finished all of the A's have been crossed off and we determine that all C's have been crossed off, then we accept, because now the product of I and J is equal to K. Otherwise, we reject. This is, hopefully, if you have followed me along, great, you would see that this would, in fact, do what we expect the machine to do. If not, then I think when you get a chance, if you walk through it yourself, you will be able to convince yourself. But I want to point out a couple things here. And the thing to point out will be about the different states. So stage one was basically making sure that A plus B plus C plus is a member, or the input actually satisfies that one. That operates much like what a finite automata would do. There was no writing necessary as the head moves to the right and the left, because it was just recognizing, and it just needed to keep track of this by having states to determine whether the input is in the proper form. So I could have asked you, and you probably would not have too much of a difficulty to try to write an NFA or a DFA that would recognize just that part of it. So we'll have enough number of states and enough transition functions to do that, and that will be easy to implement. Stage two is the place where we had to come to the left-hand end of the tape, and that would require us a little bit of thinking. But we've seen an example of how to take care of something like that in the language. In the language we saw when we called M2. We needed to know the beginning of the tape there, and we used this special symbol, and in that case we reused what the part of the tape alphabet would have been a blank symbol. We use that one. So this is one way to do it. In this case, we needed a way to get to know we have come to an end, to the left end of the tape. So because we've seen one example before, we could do something like that. There is another way, another solution to having to know, to determine the left end of the left hand end of the tape. And that one will take us back to what we had discussed in our lecture last time, when we were talking about having to prevent the machine to fall off the left hand if our transition function had said move to the left and we're already on the left end, we will not obey. That's what I told you last time. So we could rely on that definition and try to solve this problem. But I prefer the first one, where we have an explicit way in which you have devised to give a special symbol, and that is how I would probably have gone to do it if we were to fully describe this one in terms of state machines. Stage 3 and stage 4 are fairly straightforward, and their implementation should not have too much of a difficulty, but you should at least convince yourself that there are so many states that would probably be involved in these ones compared to what we have seen in the first two examples. That was my example 3. And I want to finish off with a fourth example, and we've got another 5 minutes. And this is a fun problem. And so this problem, the examples we have seen so far, each one of them kind of gives you a different flavor of the kind of thing that a Turing machine could be designed for to solve. And this one tries to solve what's called element distinctness problem. So we have an input, and this input has hash symbol and some string, and each one of these would be defined over a binary string. They could be of different lengths, but we will call them xi's. So we've got x1, x2, and it goes all the way up to xl. So the question now is, we want to design a machine in which that would check whether these elements are all distinct, that none of them is the same as the other ones. In other words, we have the language E, and it is a hash symbol followed by x1, hash symbol followed by x2, and so on. It goes up to xl, and each one of these xi is made up of zeros and ones of a certain length, repeated as needed, and xi and xj are required to be different, and this will be true for any I and j. So for any pair of x's I pick from this language, from this input, they need to be different. So this machine now, if you were to think about it, how you would go, and if you were to write a program for it, you would start by saying, I'm going to start x1 and compare it with the rest of the world, x2 through xl. If any place where I find x1 is the same as one of these x's I see, then I would say that it is not a member. Otherwise, I would continue. So that would take care of x1, and then you would continue with x2 and do through the rest. That's how M4 would work. So there is a high-level description here, and this is where I would stop. I have essentially told you what we would be doing. What we would want now to find a way is these x's themselves are, the way I described them now was at even higher level, because I was just checking one X against another X. But remember that this is a string of zeros and ones. So we'll have to go through them one at a time and then compare things, whether they are equal or different. So it becomes a little bit more involved. So we place a mark on the tape on the top of the leftmost tape symbol, because now we want to make sure that whether we are checking two things and we want to see, are they the same or are they different? And so we would want to know how to be able to tell apart. So equality between two symbols, and then I've got another equality between another pair of symbols and things like that. So we place a mark on top of the leftmost tape symbol. If that symbol was a blank, we accept it. That means now if this is going to be repeated, but if it was only one thing that we have, then we will not need to, it will be distinct, and therefore we will accept it. If that symbol was a hash symbol, now we will continue to the next stage because we've got more things to do. Otherwise, if this is not accepted, we will reject. And so we'll scan right to the next hash symbol now, because now we have got another X to work with, and place a second mark on top of it. So the first time it was one mark we used, and now we are going to put another mark on it. If no hash symbol is encountered before the blank, before we say a blank, that means we have not finished it. Then the XI was present, and so we accept it. Otherwise, we're now going to be doing zigzagging, just like what we have done in our, I think it was M2, I think we called, where we had to zigzag. And we compare two strings to the right of the marked, the ones marked by the hash symbol. If they are equal, we found the first instant where we find equality and we don't need to proceed, we reject. Otherwise, we move to the rightmost of the two marks, the next symbol, and then we continue in this fashion. And when we have exhausted this one, we would accept. There is only one thing I want to say here compared to what we did with the third Turing machine. This one has an illustration for where we have a need for having to write on the tape for symbols that are many. And so these X's are each consisting of certain lengths, and we want to make sure that they are different. And so we need to write. And so we would want to write a symbol on top of it is another way of saying to have a duplicate with one thing that will be one additional symbol. And then I have shown this with a prime on top of the hat. This is how we would alter the tape alphabet. And we'll plus this one on various symbols on the tape. And all we really need is to have twice as many of the input symbols that are needed to write on top of them. All right, I think I know I have gone a little too fast on M4, but I hope you have followed me. If there were questions that came on the group chat that I haven't paid attention, I'll take a look and try to address them. Our time is up, but if you are still around and if you're not in a rush to go to another class or something and you have a question, let me know. I'll give another 30 seconds or so if people have questions. Was this okay to follow along? Okay. Okay, thanks for, all right, thank you for attending and take care of yourselves. And when things are up, we'll post them on Oswald, but I will put the slides even before the Zoom recording comes. So I'll see you on Friday and have a good rest of your day.